So even though there were an instance or two in Chapter 1 where systems of equations could be used, and they were used to a very minor extent, um, and by primarily substitution, Chapter 2 deals with solving systems of linear equations, and actually gets into using matrices to do that as well. So um, systems of linear equations, basically, what you're often going to see them written in their expanded form, which they're showing you two expanded forms here. So given you have two equations with two different lines, there's only three outcomes that can happen with them. If the two lines, L1 and L2, then one and only one of the following can occur. Either they intersect at exactly one point, and therefore you would have one unique solution, or a set of coordinates where they intersect. They are parallel and coincident, which means basically they're the same line. And in that kind of situations, there are infinitely many solutions. And the third is that they're parallel and distinct, which means there would be no solution. Sometimes they call the second situation consistent. Well, I mean, in some textbooks, having a unique solution is consistent and independent. Having infinitely many solutions is consistent and dependent. And the two instances of parallel lines where there's no solution is sometimes called inconsistent. So we're going to be looking at circumstances involving each of these and how we're going to be able to distinguish that without necessarily graphing. But we're going to start off with the graphing for the time being. So for example 1 here, you're being asked to solve a system of equations by graphing and by an algebraic solution. Now, you're not going to be able to really do or show me any work you do on a graph, but I'll give you some time to pause and to determine what the algebraic solution is, and let me know what the solution to this system of equations would be. So graphing, one thing you'd have to do is, the easiest way to graph them is to put them into slope-intercept form and then graph them. And as you can see, I graphed the two lines, and I see that there is a solution which looks to be somewhere around 2, 4. One of the things about graphing is, I mean, first of all, you're not always going to get solutions that have integer answers. I mean, a good number of them will very well be, but you're not guaranteed to have them. And when you get situations where you have one or both answers not being an integer, that can be difficult to do with graphing, depending on how you have things scaled. So algebraic solutions are much more ideal. And up to this point, all we've really been looking at is substitution. So one way we could, I mean, since I do have both equations solved for y at this point, I could set 3x minus 2 equal to negative 2/3 x plus 16/3. However, what I could also do is just like look at one of them in its slope-intercept form and one in its expanded form, which is the one I'm going to show here, and solve that way. So you notice I'm keeping the top one as the y equals 3x minus 2, and I'm leaving 2x plus 3y equals 16 kind of where it is. And I chose that mostly because of the fact that the second one had much more fractions. And even I don't shy away from fractions, but if I recognize that one has integers and the other one doesn't, I'm going to go with the one that has integers because they're usually easier to work with in the long run. So if you look that far enough ahead, you can make such adjustments. So what you're seeing me do here is, since I know y is the same thing as 3x minus 2, I'm going to the equation, the second equation, and I'm replacing y with 3x minus 2 since they are equal to the same thing. So simplifying the left-hand side, I get 2x plus 9x minus 6 equaling 16. Combine some like terms, I get 11x minus 6 equaling 16. And then adding 6 to both sides, I get 11x equals 22. And dividing both sides by 11, x equals 2. Now that's part of the solution because I had to find a solution for the x and the y. So now that I have this solution, and I do have one equation at the very least solved for y, I'm just going to plug that x back into the y equals 3x minus 2, and I do find that the y does equal 4. So the solution is 2, 4, which looked like that's what the graph was originally. But as I said, just because it looks like it passes through integers doesn't mean it actually is. I mean, if you get an integer answer, you get an integer in ordered pairs, plug them in, make sure it works for both, and then you're good. But if you find that doesn't work, you may have to do algebra to get the exact answers. Now, what if you have infinitely many solutions? So, like for instance here, what you see is, I'm going to show a graph, and I get y equals 4/3 x minus 4, and when I do the graph of the second one around, I get y equals 4/3 x minus 4. That there shows me, when I went into the process of graphing them, that they're the exact same line. Now, oftentimes, if you're going to solve a system of equations, we're going to eventually learn about elimination, especially when it's in a situation where both of them are in expanded form. Or at the very least, when we do the method of substitution, we usually only alter one of them. So you may not notice the other one is y equals 4/3 x minus 4 because you didn't alter it around. So how do we recognize that in the case of an algebraic solution? Well, let me take you into the algebraic solution, and then I want you to try to see how you would interpret it in order to get to a point where you can say, okay, now I know there's infinitely many solutions. So if I go through the algebraic solution, I'm going to keep the top one, y equals 4/3 x minus 4. And I'm going to keep the second one, 8x minus 6y equals 24, pretending as though that I didn't alter it to already find out they're the same line. How would I recognize that if I were to go through algebraic methods of solution? Well, again, like I did before, I'm taking the y and replacing it with 4/3 x minus 4, because that's what y equals in this one. And if I simplify it, I end up getting equals 24 equals 24. And that 24 equals 24 is what allows us to say that I have infinitely many solutions. Now, the question I have for you is, why is that the case? So in your best ability, explain how and why that would indicate that that tells us we have infinitely many solutions. Okay, so the reason why we know that we have infinitely many solutions, because infinitely many solutions as well as no solutions are special cases of systems of equations. They're more times than not, if you have two linear equations and they are two different lines, they are going to intersect each other. It's only when they're the same line do I have infinitely many solutions. It's only if they're parallel lines do I know if it has no solution. So, when I solve a system of equations, first of all, I know I'm going to get a special case because both variables canceled at the same time. So if you choose a method that you say, okay, I want to somehow eliminate x's from this equation and solve for y, or do the opposite, eliminate the y's and solve for x. What you find out is when I eliminate one of the variables, the other variable it gets eliminated at the same time. That tells you you're down to either one of two possibilities. It's either going to be infinite solution or no solution. And the reason why in this case it is an infinite number of solutions is the statement I am left with is a true statement. 24 equals 24. It always does. So I was left with, I had all variables cancel. I was left with a true statement. Therefore, I know that the system is going to have an infinite number of solutions. Now, what I want you to do is do a similar explanation into this. Now, this system of equations has no solution. And if you go through the graphing, you can see, graphically, there's no solution. I mean, these two lines do not intersect each other. They are parallel. So, how would you recognize that in an algebraic solution? So let me get you started with the algebraic solution, and I want you to finish it up and explain how you know, based off of what you end up with, it's no solution. So in the instance I want you to explore here is y equals 1/2 x minus 2 is what we're going to leave the first equation. The second equation we're going to pretend as though we left it unaltered. It's still 9x minus 18y equals 30. And as you see, we did a substitution there. So carry it out the rest of the way. See what you get as an answer or as a result, and then use that to explain how you know it's no solution. Okay, so I mean, I left you at the point where we substituted for y. We have an equation with only x in there. So I continue this through. So I'm going to distribute the negative 18, and I get 9x minus 9x plus 36. The 9x minus 9x cancels. So I have 36 equaling 30. So much like we did in the previous instance, all the variables canceled. Basically, when I went through a procedure to basically eliminate the y's from the equation. When I did that, the x's got eliminated at the same time. So again, both variables cancel at the same time. The difference is this time around, I ended up with a false statement. I ended up with 36 equaling 30, which of course it doesn't. And since I'm ending up with a false statement, it's basically saying, well, the only way for this to have a solution is for 36 to equal 30, and since that's not true, this thing's not going to have a solution. So that's basically how you tell the two special cases apart. Both of them are going to have the same overall first result in that both variables get eliminated at the same time. The only difference is for an infinite number of solutions, you're going to be left with a true statement, whereas for a no solution, you're going to be left with a false statement. Any other time, you're going to be able to solve the equation for x or y, whichever one you chose to keep and get rid of, and then you're going to go back and be able to find the other value, and you'll have a set of coordinates. So, if a set of coordinates doesn't come out to be an answer because both things go away at the same time, then you're just basically looking to see if the truthfulness or falsity of the statement that's left behind. So, now most of the time when you're given situations like this, now this problem is involving a circumstance where there's a system of equations needed. Because you're looking at children, students, and adults in this theater. So, as you do this, you're going to come up with a system of equations, and you want to be able to solve it. And typically, application problems, there are going to be circumstances where there's going to be a solution. Every once in a while, they might throw one at you where there's not going to be a possible solution for the circumstance. Or you're saying that this was describing an impossible event, which can happen, but usually for application problems, that isn't the case. The only thing I'm going to give you a hint on, and I'm going to give you a chance to run through and solve this really quick, is that there's three different things here, and basically you're given information about children tickets, student tickets, and adult tickets. Ultimately, I want you to figure out how many children attended the show. So it's not really asking you to find out how many of each group attended the show, just the children. So that may dictate how you choose to, eliminate variables and which ones you're going to be left with. So, but the idea is you have three different variables here. You're going to need three different equations that relate them together based on the information. So take a few moments, read through this problem, write out a system of equations, and go through the process of solving it, and let me know how many children attended the show. Okay. So, as I mentioned before, we do have children, students, and adults in this problem. So, I'm going to let C represent the number of children, I'm going to let S represent the number of students, and I'm going to let A represent the number of adults. Now, we know that there's a seating capacity of 900, and we're told that the screening had full attendance, which means all 900 seats should have been taken up. So, that's where my first equation is going to come from. I know that the number of children plus the number of students plus the number of adults is 900. The next thing I'm going to be using is that, they're giving us the cost for a child seat, the cost for a student seat, and a cost for an adult ticket. So I'm going to use it, and I know that the receipts totaled $5,600. So basically, if I want to figure out how much money I earned from each group, much money I earned from children tickets, student tickets, and adult tickets, 4C would represent the amount of money I would have gotten from children tickets. 6S would represent the the amount of money I earned from student tickets, and 8A would represent the amount of money that I earned from adult tickets. If I add all those up, that should total the $5,600 that we had in total. So there is my second equation. The third equation is going to come from the statement that's kind of in the middle there. It says at a certain screening with full attendance, there were half as many adults as children and students combined. So using that, the number of adults equals 1/2 C plus S. That substitution is going to help me, come up with two equations with just C and S. And then I'll take those two equations and just get it in terms of C. And that's the way I'm going to kind of go with it, because that's all I'm trying to figure out is what C is. So I'm plugging the 1/2 C plus S in for A. So in the top equation, A is just replaced with 1/2 C plus S. Same thing in the second equation, but since the A was multiplied by 8, I have the A being multiplied by 8. So as a result, the first equation, if I simplify it, becomes 1.5C plus 1.5S equals 900. And the second equation, once I do my 8 times a half and I add like terms, I have 8C plus 10S equaling 5,600. Now, usually I would typically do elimination in a situation like this because it's just a little easier with this. But since we haven't talked about that yet, I'm going to take the first equation. I'm going to subtract 1.5S from both sides, or 1.5C from both sides, and divide both sides by 1.5, and I would end up with S equaling 600 minus C. So again, I subtract 1.5C from both sides, and then I divide both sides by 1.5, making sure I distribute both terms. And now I have a term that I can replace S with. So 8C plus 10S equaling 5,600 can now be 8C plus 10 times 600 minus C equals 5,600. I simplify that. I'll subtract 6,000 from both sides, and I'll divide by -2. And I get that C is 200, which means that there were 200 children attending the show. So even though we discussed infinitely many and no solutions, we're going to take a small break and just focus our attention on unique solutions, because in section 2.2 we're going to learn the other method that I mentioned before about solving systems of equations using elimination. We're also going to get into dealing with some matrix stuff as we move along into it. So the elimination method are basically, we're going to keep the equations in expanded form. And as long as we do one of these three things, we're not changing the possible equations at all to anything that's going to make the answers change. So basically, if I choose to interchange any two equations, which is kind of more of a substitution, but basically that means, okay, instead of having one on top and one on the bottom, I could just move that around. I don't really need to do that a whole lot. It's kind of silly to do that for two equations and two unknowns. It's something that gets done more often with three equations and three unknowns, because sometimes I have to take just two of them at a time and choose to eliminate a variable. The other thing I could do is I can replace an equation by a non-zero constant multiple of itself, which means basically I could take any equation that's in there and multiply the entire equation by a constant. And 3, I can replace an equation by the sum of that equation and a constant multiple of another equation to come up with yet another equation. And so, what we tend to do is we add equations together in a way where I can eliminate a variable by doing so. So let me demonstrate what that looks like, because it makes more sense when you see it in action. So in example 1 here, you're being asked to solve the following system of equations using elimination. So let's do one at a time. So we're going to look at the first equation. And what I do is I make a decision about which variable I'm going to eliminate. Now, it doesn't matter which one you choose to eliminate. I could choose to eliminate x's, I could choose to eliminate y's. It really doesn't matter. But in some instances, one's easier than the other. In this case, I'm going to eliminate x because I can easily, multiply the top equation by a constant to get any value, any like constant times x I want, because currently there's a 1 there. Now, when I choose to multiply the top equation by depends upon what I'm going to do with it. What I want to do for x to be eliminated, I want to get the same number in the top equation in front of x as I have in the bottom equation, but I want it to have a different sign. And since the bottom equation has a positive 2x multiplied to the x, I'm going to multiply the top equation by negative 2. That'll put a negative 2 in front of the x, and so eventually when I add the two together, the two equations that is, the x's will get eliminated. I just can't multiply the x part of an equation by negative 2 because that's going to alter the equation, or to alter the solution of the equation. So what I'm going to do is multiply the entire equation by negative 2. So the top equation is going to become negative 2x plus 4y equaling 6. The bottom equation is left unchanged. The reason why I chose to eliminate the x on this is if I chose to eliminate the y's, I'd have to multiply both equations by a constant and alter both of them. At least this way, I only had to alter one of them. So sometimes that's what helps you make the decision about which is easier than the other. But now when I add the two equations together, the x's get eliminated. Well, that's why I did that. When you get to the stage where you add the two equations together and one of the variables doesn't disappear, then you're not doing it right. And as a side note, don't make them disappear just because that's what you want them to do. You have to make sure they're in a position to disappear. When I add the two equations together, because a lot of students will take the top equation, multiply it by 2, and they say they're going to add them together, and they'll say that 2x plus 2x is 0x, and they cancel. Well, they wouldn't. If you were subtracting the two equations, but that would require you to do some distributive property things. But anyway, if I add the rest of it, I get 7y on the left-hand side equaling 14. I would divide both sides by 7, and y would equal 2. Now that I know what y equals, I can go back to one of the two original equations. It really doesn't matter which one. I can replace the y with a 2. So I did it to the bottom equation. So 2x plus 3 times 2 equals 8, which means 2x plus 6 equals 8, which means that 2x would equal 2. And dividing both sides by 2, I get that x equals 1, which means that the solution is 1, 2. So, when you get to a 3 by 3, I'm going to start you off on this, but then I'm going to have you complete it, because when I use eliminations, when I have 3 unknown values, or even more, I mean, the more variables and equations I have, the more I have to kind of do this process to eliminate one variable at a time. When I look at these 3 equations, I'm going to choose, to group these equations as so. I'm going to take the first and second equations. I'm going to do the first and third equation. I'm going to do the second and third equation. And I'm going to choose to eliminate y. Mostly because I notice that in the third equation, y has a 1 in front of it, a negative 1 technically, which means I can alter y pretty easily, and that's all I need to do with it. So I chose to eliminate y on both equations. So on the first set, on the third equation, I multiplied it by 3, and that would make the y's disappear when I eventually add them. And I multiplied the third equation by negative 2 for the second set. And what ends up happening when I do that and I add the equations together, I get 14x plus 7z equals 7, and I have negative 5x minus 4z equals 2. So now what I have is I have now two equations with only two of the variables in it, which gets us back to a circumstance that we had before. So from this point on, I'm going to want you to give this a try. I want you to solve that system of equations, 14x plus 7z equals 7, and negative 5x minus 4z equals 2. I want you to solve that and use what you get there to help you figure out what the values for x, y, and z all are. All right. So now, how you chose to go about doing this may be varied differently because of the fact that of the two equations I have now, I could either eliminate x or I can eliminate z. It's really up to you. I chose to eliminate z for the sole purpose that the numbers would be a little smaller to deal with than trying to find a common multiple between 14 and 5, which the only one would be multiplying 14 and 5 together because 5 is a prime number and 5 is not a factor of 14. So I chose to multiply the top by 4, and I chose to multiply the bottom by 7 because I'm eliminating z, and the z's already have opposite signs, so I don't have to worry about a sign change with this. All I have to worry about is getting the same number in front of the z's with opposite signs. The opposite signs are already there. So if I do that, I get 56x plus 28z equals 28 for the first equation, and I get negative 35x minus 28z equals 14 for the second equation. Now when I add the two equations together, the z's, of course, do cancel. They're eliminated. And I'm left with 21x equaling 42. I divide both sides by 21, and I get that x equals 2. Now that I know that x equals 2, I can go back to one of these two equations that I came up with before and substitute the x value in there to find z. So I chose this one here. I replaced x with 2. 14 times 2 plus 7z is 28 plus 7z. I subtract 28 from both sides and get that 7z equals negative 21. Dividing both sides by 7, I get that z equals negative 3. So now I know x equals 2. I know that z equals negative 3. I can now go back to one of the original three equations here and replace the x with 2 and the z with negative 3 and see what I get. So I chose to take these two and plug it into the very first equation. So the 2 replaced the x, the negative 3 replaced the z. So I have 2 times 2 plus 3y minus 2 times negative 3 equals 10, which is 4 plus 3y plus 6 equals 10, which means that 3y plus 10 equals 10. 3y would equal 0. Dividing both sides by 3 would give me 0. So my solution would be that x equals 2, y equals 0, and z equals negative 3, which of course I could write the solution as an ordered triple, 2, 0, negative 3. So that is the elimination method. The elimination method can get quite a bit tricky when you have, as you see here, 3 unknown values in 3 equations, or 4 unknown values in 4 equations. It would require a lot of smaller steps. There is using augmented matrices, however, I could do that, some of the same things, but just it's a little bit more compact and a little easier to do all the things that need to be done. So the first part comes into writing it as an augmented matrix. Now I'm not going to have you do this on your own. And the example 2 is just actually say example 3 or 4 at this point, but for some reason it still says example 2. Writing these as augmented matrices is not a hard thing to do. Basically, all you're going to do is take the coefficients from the left-hand side here and write that on one side of a matrix. you're going to put a bar like right here, and you're going to put the numbers on the right-hand side here. When you do that, though, you have to make sure your x's, your y's, and your right-hand sides are all lined up. And much the same would be, same thing. I mean, anything that doesn't have a number in front is going to have a 1. Keep that in mind, otherwise the variable wouldn't be there. And if a variable isn't there, you replace it with a 0 in the matrix. So for this one here, I'm going to have a column of 2, 3, 4, 3, -2, -1, -2, 2, and 3, the bar, and then 10, 0, -1. So doing the augmented matrices is not a hard thing to do. That's not the hard part. The hard part is going to come from doing what we call row operations so that we can get something that's in a row-reduced form of a matrix. Sometimes it's called reduced row echelon form. So, a row-reduced form of a matrix, one has each row consisting entirely of zeros lies below any other row having non-zero entries. The first non-zero entry in each row is 1, called a leading one. In any two successive non-zero rows, the leading one is in the lower row lies to the right. They're giving you this really long description, but basically, to show you, if I were to have a matrix that's 2 by 2, and these have to be square matrices, by the way. A 2 by 2 square matrix looks like this for a row-reduced form. A 3 by 3 looks like this. A 4 by 4 would look like this. Basically, all I'm going to have are 1s and 0s, and the 1s start at the upper left-hand corner of the matrix and move in a diagonal pattern until it reaches the bottom right. So essentially, you'll see them sometimes even represented as 1, 0, dot, 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 0, 0, 1, dot, 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 0, and they'll say dot, they'll do all these little dots and stuff like that. To eventually have 0, 0, dot, 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 1 here. And they kind of show it like that, showing that you're going to have a diagonal of 1s and all the other row column entries are going to be 0s. That's what they call row reduced form. And that's what we want to end up with on the left-hand side. Because remember, each column represents usually a variable. Okay, so if I have 1x, 0y's, 0z's equaling a number, well, that means that x equals that number. So, and, but the thing is, you have these row operations to do it, which looks a lot like the elimination rules. I can interchange any two rows because that's the same thing as interchanging two different equations. I can replace any row by a non-zero constant multiple of itself. So I can multiply any row by a constant. And I can also replace any row by the sum of that row in a constant multiple of any other row. So it's kind of the same thing I do with elimination, and that's why they call this usually like, matrix elimination method. So, and that's what the Gauss-Jordan elimination method does. It's basically, when you take an augmented matrix and you make the left-hand side into a row-reduced matrix, that's basically what you're doing here. The trick of doing this is, even though these are what you're allowed to do, and they're showing you like the context, the symbolism that you would use to do it. Like if I have like a row, like row 1, double arrow, row 2, it means I'm interchanging those two rows. If I have a number times row whatever number it is, I'm replacing that row with a number times that row. And this one's very important too, the last one. If I start with, if I have row I plus a multiple of row j, means I'm replacing row I with the sum of row I plus that multiple of row j. Which, I mean, so, and it doesn't have to be a consecutive rows. I could take the first row and add it as a multiple of the fourth row, or whatever it may be. Um, the thing is that students sometimes have trouble with this, is that you have to do this in a very specific way. Otherwise, you could possibly have row operations that will undo the effects you wanted to have in any other row operation. So let me demonstrate for these two. This is the same 2 by 2 matrix we had before. So, let's see here. So, no big deal about that. I mean, we should get the same answers we had before. So, I'm going to rewrite this and as an augmented matrix. And now what I want to do is get this side here. If I can get my cursor over there. Come on. There we go. I want to get this row, this side right here to be that 1, 0, 0, 1. I mean, so that's what my goal is. My goal is to make it look like that. I already have the 1 in the upper left-hand corner, so that's one less thing I have to do. What I want to do now is that's the way it works. I establish the 1 where I need it for a given column first. So I do row operations to alter each column, going column by column. So I want column 1 to get this 1, 0 look to it. I have the 1, I want a 0 down here. The row operation I am typically going to use to get a 0 in the position I need it to is to replace the row I'm looking at, in this case row 2, with a multiple of any other row in the matrix. We only have one other row here. So if I were to take 2 and add it -2 times this 1, I would get a 0 there. Well, that's what I'm going to do. I'm going to take row 2 and I'm going to multiply. I'm going to basically add a -2 times row 1, or basically say here I'm taking row 2 and subtracting 2 times row 1. Remember, in algebra, adding and subtracting are considered to be the same. They're the same in the precedence of order of operations because they're the same operation. All subtraction is essentially adding a negative. So, so this is legal. So if I take this 2 and subtract away 2 times 1, I do get the 0. 3 minus 2 times -2, well, 2 times -2 is a -4. If I take 3 minus a -4, that's 3 plus 4, that's 7. 8 minus 2 times -3. 2 times -3 is -6, so 8 minus a -6 is like the same thing as 8 plus 6, that's 14. So now I have this column. The next thing I want to do is establish a 1 down here. The best way to establish my 1s is that's where I usually am going to multiply by a constant times the row. So here I'm going to take row 2 and multiply it by 1/7, which is the same thing as dividing by 7. So if I do that, now row 1 is unaffected. Now we get the laser pointer thing going on here. 0 times 1/7, nothing happens. And that's what I want to have happen. Once I get that 0 here, and once I have this column established, any change I do from here on out should leave that column alone. If I am not doing that, if that's not happening, if I get that column to change in any way, I'm undoing some of the things I've done before, and I'm not going to get the answer I'm looking for. 7 times 1/7 is 1. 14 times 1/7 is 2. So I got this right here. Now, this is what we would call reduced form. And actually right now, I have a statement that says 0x plus 1y equals 2. So I know what y equals. I could find x at that point if I wanted to. But they want you to put this in this form so that when I have the end of product, I can say I have 1x equaling a number, 1y equaling a number, so I know what they are. So now I want to get this to be a 0. Well, again, to get zeros, that's when I add a multiple of another column. So I want to take row 1 of another row. So I want row 1 to be replaced by row 1 plus 2 times row 2, because if I take negative 2 plus 2, I'm going to get that 0. And so that's what I'm going to do here. I'm taking row 1 and I'm adding 2 times row 2. So if I take 1 plus 2 times 0, I'm still going to end up with 1. Good, that's unchanged. I don't want that to change. If I take negative 2 and add 2 times this, well, I'm going to get that 0. Well, that's what I wanted there. Negative 3 plus 2 times 2, well, 2 times 2 is 4, so negative 3 plus 4 is 1. So I have 1, 0, 0, 1 on the left. I have 1, 2, which means, again, at this point, I have 1x plus 0y is equaling 1, which means x equals 1. And I have 0x's plus 1y equaling 2, which means y equals 2. And I get the same solution I had before. And that shouldn't be no big surprise, because I should get the same thing I had before. So now I'm going to have you try this system of equations again, but now I want you to use this other method. I mean, you know what the answer is, because if you look back to a previous example, we've already worked this out using elimination. But what I'm hoping that you see is that, this keeps things a little bit more compact. Doesn't necessarily take away the amount of work you have to do. It's just a different method of doing it. So again, we're going to use the augmented matrix, which we established beforehand, which is this right here. And our goal is to get that left-hand side to look like this, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that's what we're looking to get here. So, so what you want to do is carry through the row operations that would make that happen. Some of it may depend upon what you choose to do. I mean, you could interchange rows, but it's really, the only time I really interchange rows is if I have a 1 in the place that, if doing so will put a 1 in a position where I need it to have, or put zeros in the places where I need to have it. I mean, those would work. But generally, I'm usually not going to have enough information, to do a whole lot of row swapping to help me out. I'm usually going to focus my attention on either multiplying a row by some constant, and those are usually to establish my 1s, or I'm going to be adding a row by a constant times another row in order for it to be, changing a certain number in that row to a 0 that I need it to be. So do your row operations, see what you come up with to get to the answer, and then we'll go over this momentarily. Okay, so again, there could be variations to this, but this is how I approach doing it. So keep that in mind if you did some other similar things, but went some different routes with it, that's fine too. The first thing I did is, I obviously want to turn the 2 in the upper left-hand corner into a 1. So I'm going to take the entire row 1 and essentially divide it by 2, or multiply by half, same thing. So my first row becomes 1, 1.5, negative 1, and a 5 on the other side of the line. The other 2 rows were unaffected because I didn't do anything to them. So I established the 1 where I need it to be. Now I need the 3 and the 4 underneath that 1 to become zeros. And I'm going to do that by taking row 2 and row 3 and adding some multiple of row 1 to it. So row 2, I'm going to take row 2 and subtract away 3 times row 1. I'm going to take row 3 and subtract away 4 times row 1. And I did both of those together. I mean, technically they're 2 different row operations, but row 1 is being unaffected. I'm only using row 1 to get a multiple of it. If I'm taking row 2 and subtracting 3 times row 1 from it, I'm going to get a change in row 2. Same thing with row 3. So if I carry through those operations, 3 minus 3 times 1 is 0. Negative 2 minus 3 times 1.5 is a negative 6.5. 2 minus 3 times negative 1 is 5. 0 minus 3 times 5 is a negative 15. 4 minus 4 times 1 gives me the other 0. Negative 1 minus 4 times 1.5 gives me negative 7. 3 minus 4 times negative 1 gives me 7. And -1 minus 4 times 5 gives me a -21. So I've established my column 1 with the 1, 0, 0 I want. Now, any row operations I do after this point, that column should remain unaffected. If I'm doing something that makes that column change in any way beyond it being the 1, 0, 0 I have going from top to bottom, then I'm doing some incorrect row operations. So the next thing I want to do is I want to establish the 1 I should have right here. So what I want to do is essentially divide row 2 by a -6.5, which is the same effect as me, if I get to work, taking -2/13 times row 2. So 0 times -2/13 remains 0, unchanged. -6.5 times -2/13 will give me the 1. 5 times -2/13 gives me a -10/13. And -15 times a -2/13 gives me a positive 30/13. Get some nasty fractions here, and oftentimes when you're using this method you will, but it's still keeping things rather organized. So now I've established the 1 down here. I want to make this and this zeros. So I'm going to take row 1 and add it by a multiple of row 2, and I'm going to do the same thing with row 3. So essentially, since 1.5 is 1.5, I'm going to make that at 0. I'm going to take 1.5 minus 1.5 times 1, which tells me I'm going to be doing row 1 minus 1.5 times row 2. In the very similar nature, I want -7 plus 7. That'll cancel, become a 0. So I'm going to do row 3 plus 7 times row 1. And that's what my two row operations are. And when I carry them through, these are what I get. I get my column of 0, 1, 0 here. This becomes a 2/13. This becomes a 21/13. This becomes a 20/13. This becomes a -63/13. Row 2 was left unchanged because I just used a multiple of row 2 to help me. Now again, when I carry through any other row operations to the rest of this problem, this column as well as this column should remain unchanged. If that's changing as I keep doing more work, I'm doing incorrect row operations, or I'm not doing them in the proper place at the very least. So now I want this to become the 1 that needs to be at this corner. So to turn this into a 1, I would multiply it by 13/21, which means I'm going to take this entire row and multiply it by 13/21. So when I do that, I get the 0, 0, 1 here. -63/13 times 13/21 becomes -3. So I have my 1 established in column 3. Now I need these to become 0 and 0. So the row operations I choose to do is I'm going to take row 1, which has the 2/13. I'm going to subtract that by 2/13 times row 3 because that has the 1 in it. And I'm going to take row 2, which has a -10/13, and I'm going to add 10/13 times row 3 because -10/13 times 10/13 times 1 would make that a 0. So if I carry through these operations, I do get that format on the left-hand side. The 20/13 minus 2/13 times -3 is going to give me 2, and the 30/13 plus 10/13 times -3 gives me a 0. So again, I have the x, y, and z that I had there before, so my solution is still going to be 2, 0, -3. So it's the same procedure as before. Now the thing is, so you can see when we do this type of row operation stuff, we can recognize when we have unique solutions. But what happens now if we have an underdetermined or overdetermined systems, which means these are systems that either have no solution or infinitely many solutions? If a system, we talked about this before, systems with no solution. We talked about if there's a row in an augmented matrix containing all zeros to the left of the vertical line and a non-zero entry to the right of the line, then the system of equations has no solution. So basically, if we have a row of zeros on the left-hand side, on the right-hand side of the bar, there's a number other than 0. That's no solution. And if that number happens to be a 0, that means that more than likely it's going to be infinite solutions, but it gets harder to tell the more equations you have and more unknown values. That may not necessarily be the case. So, and we talked about this before. Basically, if the number of equations is greater than or equal to the number of variables in the linear system, then the following is true. So basically, a system of equations can either have no solution, exactly one solution, or infinitely many solutions. If there are fewer equations than variables, then the system either has no solution or it has infinitely many solutions. What that means is if I end up finding out that, as I work it out, if I end up having several with the same equation in the long run, or they produce the same line, then that's going to create a circumstance like we were mentioning in B, and then you're going to have either no solution or infinite number of solutions. So I want you to take a moment here, and for part A, write or solve the system of equations using elimination, and see what you end up with an answer. So for part A, I chose to eliminate x's. No other reason. I mean, 10x and 4x is. I mean, there's not. I mean, I'm going to have to alter both of them. And I did the same thing for 15 and 6, but I chose to eliminate x's. So, and I noticed that 10 and 4 they share, and they're both factors of 20. So I'm going to take the top times 2, and the bottom times -5, because that'll put a 20x on top and a negative 20x on the bottom. And if I add those two equations together, they're going to cancel. If I carry that out, though, you can see what happens. The top equation goes 20x plus 30y equals 50. The bottom equation goes negative 20x minus 30y equals a negative 50. When I add the equations together, the x's do cancel. They're eliminated, but so are the y's. I mean, both of these are gone, because I have no x's, no y's, so I have 0 equaling 0. Much as it was before, this is a special case. We know it's going to either have infinite solutions or no solutions. And the fact that 0 over 0, 0 equals 0 is a true statement, that means it's going to have infinite many solutions. Now it's your turn to try B. What is the solution to that system of equations? Now for part B, if I was given that in that format, notice where the equal sign is on this one, I may have been inclined to divide both sides by 4 of the bottom equation and use substitution. But since it does say use elimination, what I first did was I rewrote the bottom equation so that I could, have it written in elimination format, which means my x's and y's have to basically, line up. So I subtracted 6x from both sides, and I have negative 6x plus 4y equaling 5 for the bottom equation. And again, I just arbitrarily picked a variable to eliminate. I chose to eliminate, I looked at the y's, and I said, okay, I'm going to eliminate the y's because all I have to do is multiply the top equation by 2, and if I add them together, the y's will cancel. So I multiply the top equation by 2, and I end up with 6x minus 4y equaling 8. The bottom equation remains negative 6x plus 4y equaling 5. And so when I add these together, the y's do cancel. I'm left with no y's, but I'm also left with no x's. To the right-hand side, 8 plus 5 is 13. So basically, I end up with both variables cancel, and I'm left with the statement that says 0 equals 13. Well, because of that, again, I had both variables canceling at the same time. That tells me I have a special circumstance, one of those special cases. And since I'm ending up with a false statement, that tells me that there is no solution. So that's how you can tell with elimination. It's very similar to what happened with substitution when we had the same kind of circumstances. How do you tell with these other methods, using the augmented matrices and Gauss-Jordan elimination? So using the same systems, when we know what the results are, if I rewrote A as an augmented matrix, I would do 1/10 row 1 and get, the results I see there. I would do row 2 minus 4 times row 1 and get this result right here. And here's where we have an issue. On this side right here, I have a row of zeros. And what I have is basically telling me that 0x plus 0y equals 0, which makes sense. Basically, having a row of zeros to the left of that vertical bar means that all the variables have canceled. And if all the variables have canceled and I add them together, which means there's nothing in their places, then I end up with nothing. Well, that's a true statement. So that would tell me infinitely many solutions. So for B, again, we'll start with the augmented matrix, as we had to convert it to this, and we use the augmented matrix. So first, what would be the first row operation you would do for this? Well, with what I have here, I want a 1 in this position up here, so I'm going to take row 1 and multiply it by a third, divide by 3, whichever one I say, and I end up with this. I want a 0 where this -6 is. So what row operation am I going to do next in order for me to make what's -6 here into a 0? So yes, if I add 6 times row 1 to the new row 1, this one right here, to row 2, then I would get that 0 where I need it to be. So row 2 plus 6 times row 1. But when I do that, though, -6 plus 6 is 0. 4 plus 6 times -2/3 is the same thing as 4 plus a -4, which is 0. And 6 times 4/3 is 24/3. 24/3 is 8. So if I do 5 plus 8, I get 13. Well, what I have here on the left-hand side is that row of zeros again. So I have 0x's plus 0y's equaling 13, which means 0 equals 13, because I have neither x's nor y's equaling, and totaling together is 13. So I have nothing equals something. That's no solution. So now I want you to give this one a try. I want to see you try to solve this system of equations using row operations and see what you get as a result. Okay, so again, the steps I'm going to take are that I'm going to rewrite this as an augmented row matrix. And what I'm going to do for this one here is I actually here interchange row 1 and row 2. Because I notice there's a 1 in this position. If I had that in the upper left-hand corner, that would be great. So I interchanged them. So I took row 2, put it where row 1 was, and vice versa. And now I have the 1 where it needs to be. The 2 and the 5 here and here need to become zeros. I need to have that column being 1, 0, 0. So I'm going to take row 2, subtract away 2 times row 1. And I'm going to take row 3 and subtract away 5 times row 1. And that would give me the 2 zeros I want, and these would be the results I see elsewhere. Excuse me. If you look very carefully, even here, if you're looking and paying attention, I have the exact same left-hand side here equaling 2 different right-hand sides, which means I would have essentially one set of variables equaling 2 different results. It could kind of somewhat happen, but really shouldn't. So it's kind of telling me that I'm going to have a special case, but let's carry this on a bit further. So now I'm going to choose to make this into a 1. So I'm going to multiply the entire row 2 by 1/3. And this is what I get. Now that I have this 1 here, I want to get 0 here and 0 here. So I'm going to take row 1 and add 2 times row 2 to it. And I'm going to take row 3 and subtract away 3 times row 2 to it. And what that does is it gives me the zeros here and here. It gives me that. So these two columns should remain untouched as I can proceed to the rest of the problem. The 2 plus 2 times negative 7/3 became a negative 8/3. And the negative 7, or the 3 minus 3 times, or no, so the negative 7 minus 3 times negative 7/3 gives me 0. And I'm trying to think of anything else here. And negative 7 minus 3 times negative 7/3 gives me another 0. So basically, I end up with this row where I have nothing but zeros on the left-hand side, and I have a 2 on this side. So basically, I'm being told that no x's plus no y's plus no z's equals 2, which means that 0 would have to equal 2, which it doesn't, so there would be no solution. So this is the end of this video. If you have any further questions, please make sure to bring them up in class. Until next time, have a good day.